Okay, hello everyone. In a new video. In this one we are going to explain part 2 of chapter 1 in the first unit, which is the unit of optics. The title of this chapter is lenses. Now we have reached section 4, which is nature of a lens. In this table we have on the left the properties of a converging lens, and on the right the properties of a diverging lens. So we will compare the properties of each, and these properties are very important because they will allow us to distinguish between a converging and a diverging lens. However, most of these properties we have already discussed while defining the lens and constructing its optical system. Then if you missed watching video part 1, I suggest that you go and watch it first, then refer back to this one. Then let's start by discussing the properties. And the first property is that a converging lens is thicker at the center and thinner at the edges, and this is known as a thin edge lens. So a converging lens is thicker at the center and thinner at the edges. Whereas for a diverging lens is thicker at the edges and thinner at the center, and this is known as a thick edge lens. So it's thicker at the edges and thinner at the center. Okay, we have discussed this property while defining a lens. Now the next property is that for a converging lens the focal length is positive, whereas for a diverging lens the focal length is negative. Also we have discussed this property while constructing the optical system of each. Now the third property is that the emergent ray emerges from a converging lens toward the optical axis. Okay, first of all, we call this incident ray, we call this ray to be the incident ray because it's hitting the lens, and we call this ray to be the emergent ray because it's coming out from the lens. Notice that here the emergent ray emerges toward the optical axis and not away. This is away from the optical axis, and whenever the emergent ray emerges toward the optical axis, this means that the used lens L is a converging lens. Notice that here the direction of propagation of light is not indicated, but from the arrows we can know that the direction of propagation of light is from left to right. Okay, therefore the emergent ray emerges from a converging lens toward the optical axis. As for the diverging lens, we have the emergent ray emerges from a diverging lens away from the optical axis. Okay, so this is the incident ray because it's hitting the lens, and this is the emergent ray because it's coming out from the lens. Notice that because the lens L is a diverging lens, then the emergent ray emerges away from the optical axis. So this is the third property. Now the fourth property, for a converging lens the incident ray and the object focus are on the same side. So this is the incident ray and this is the object focus. They are on the same side of the lens. This side is known to be in front of the lens, and this side is behind the lens. Okay, and for sure this lens is a converging lens. Remember that when we have constructed the optical system of a converging lens, we have stated that because the direction of propagation of light is from left to right, and the lens that we are using is a converging lens, we place the object focus on the left and the image focus on the right. Therefore the incident ray and the object focus for a converging lens are always on the same side. Whereas for the diverging lens, because the direction when we have constructed the optical system, we have mentioned that because the direction of propagation is from left to right, and the lens that we are using is a diverging lens, we place the image focus on the left and the object focus on the right. Therefore the incident ray and the image focus in the case of a diverging lens, they are always on the same side. Okay, so I repeat, in the case for a converging lens, the incident ray and the object focus are on the same side, whereas for a diverging lens the incident ray and the image focus are on the same side. Okay, now we can say also that now we have reached the fifth property. So 1, 2, 3, 4, 5. Now we are in the fifth property. Now what about the emergent ray? For a converging lens, the emergent ray and the image focus are on the same side. Okay, so let me see. For a converging lens, the incident ray and the object focus are on the same side, and the emergent ray and the image focus are on the same side. Okay, and in the case for a diverging lens, the emergent ray and the object focus are on the same side. So till now, all of these properties we have seen while constructing and defining the lens, constructing the optical system of lens and defining it. And now we are going to introduce three more properties that are new for us and we didn't discuss earlier. The first one is that an incident beam emerges from a converging lens as a converging beam. Okay, so what does the word beam means? A beam is a set of light rays okay, and the word converging here, it means that reaching a point, reaches a point. So an incident beam emerges from a converging lens as a converging beam. This is the incident beam. Notice that this beam consists of set of light rays. Because the lens here that I'm using is a converging lens, then each ray, I suppose that this is the optical axis here, then each ray will emerge toward the optical axis. So all of these rays are emerging toward the optical axis like this. Because this emergent beam is reaching a point here, so we call it a converging beam. Okay, therefore an incident beam emerges from a converging lens as a converging beam, whereas for a diverging lens, an incident beam emerges from a diverging lens as a diverging beam, and the word here diverging means that spreading away or spreading out. Spreading. Okay, so notice that this incident ray will emerge away from the optical axis, as well as this one, as well as this one, and the same for this. Suppose that this is the optical axis like this. So the incident beam emerges as a diverging beam, which means it's spreading away. Okay. Now the seventh property, which is also new for us, is that a converging lens can be used as a magnifier. One can determine the nature of the lens from its use. If the lens can be used as a magnifier, so it's a converging lens. Notice that the used lens is giving a magnified image of the text, so it is a magnifier, which means it's a converging lens. However, a diverging lens cannot be used as a magnifier because you can see if we try to read the text using a diverging lens, it will give an image of the text which is smaller in size. Okay, but we know that a magnifier give an image of the text which is larger in size. Finally, the last property is that a converging lens can form a real image which can be collected on a screen, and for a diverging lens, it can only form a virtual image smaller than the object. Okay, yet I didn't define what's the meaning of a real image and a virtual image. So far, now let's take this property for granted and memorize it. Later we will refer back to it and explain it. Now it's convenient to solve some exercises as a direct application on what we have discussed so far to check whether we have understood the concepts or no. So exercise number 1, each of the documents 1 and 2 shows a lens L, its optical axis x prime x, its object focus f, and its image focus f prime. Using the indicated scale, calculate the focal length f for each. So let's start by document 1. Okay, in document 1 we have the position of the optical center O, which is the intersection between the optical axis and the lens L, and we have the position of the image focus f prime. Therefore, we can calculate the focal length referring to its definition. Always whenever we need to calculate the focal length, as a first step, we always start by writing the definition, and it's given by the focal length is the distance from the optical center to the image focus. Now the focal length is denoted by small f, which is the distance from the optical center. In this case it's the point O to the image focus, which is the point f prime. And we don't forget the bar because this distance may be positive or negative. Now f is equal to O f prime bar, which is the distance from the optical center to the image focus. Notice that this distance is in the same direction of the positive x-axis, therefore it's positive. And now we count the number of divisions between O and f prime. We have 1, 2, 3, 4. And we multiply by the scale along which we have counted the number of divisions, which is scale along the x-axis. This will give me 12. Since the scale is in centimeters, then the value of f will be in centimeters. Always, all quantities in physics must have unit, and whenever we are taking data from the graph, we always multiply by the scale. Okay, so finally it's a good habit to write our final answer in the box to make the task easier for the corrector to notice our correct answer. So notice that here the focal length is positive, and the lens here that I'm using from its symbol is a converging lens, which verifies that the lens L is a converging lens, because we know that for a converging lens the focal length is always positive. And now as for document 2, we also need to calculate the focal length of the used lens. So let's write the definition also. The focal length is the distance from the optical center to the image focus. So the focal length is denoted by small f, and it is the distance from the optical center, which is the point O, to the image focus, which is the point f prime. And we don't forget the bar because this distance may be positive or negative. So now f is equal to O f prime bar, which is the distance from the optical center to the image focus. Notice that this distance is in an opposite direction of the positive x-axis, therefore it is negative. And now we count the number of divisions between O and f prime. We have 1, 2, 2.5. And we multiply by the scale along which we have counted the number of divisions, which is scale along the x-axis. And this will give me minus 10. Since the scale is in centimeters, then the value of f will be in centimeters. So f is equal to minus 10 centimeters. So notice that here the focal length is negative, and from document 2 we can see that from the symbol of the used lens, the lens L is a diverging lens. So the focal length is negative, which verifies that the used lens L is a diverging lens, because we know that for a diverging lens the focal length is always negative. Here in exercise number 2 they are telling me each of the documents 1, 2, 3 and 4 represent a lens. Determine the nature of each of the given lenses L1, L2, L3 and L4. Okay, so in each document they gave me a lens in which we can notice a property of the lens, and from this property we need to determine the nature of a lens. Okay, let's start by document 1. In document 1 they gave me a lens L1. Now notice from the shape of this lens it's thicker at the edges and thinner at the center. We know that whenever the lens is thicker at the edges and thinner at the center, this is known to be a diverging lens. Therefore we can say that. Okay, moreover I want to say something here. They told me determine, and determine means that I need to justify, okay? And always all answers are better if they are justified. Now, since a diverging lens is thicker at the edges, sorry, and thinner at the center, and this is known as thick edge lens. Then L1 is a diverging lens. This is it for document 1. Let's move to document 2. Okay, in document 2 they gave me a lens L2. These arrows indicate that the direction of propagation of light is from left to right. Notice that this beam emerges from a lens as a diverging beam, and we know that when the emergent beam is a diverging beam, then the used lens is a diverging lens. We can say that since the incident beam emerges from the lens L2 as a diverging beam, this means that L2 is a diverging lens. Now as for document 3, here in document 3 we have a lens, and as we can see we are trying to use the lens to read the text. The image of the text here, indicated here, is larger in size of the real text. Therefore this lens acts as a magnifier, and we know that only converging lens can act as a magnifier. Therefore the lens L3 is a converging lens. Since a converging lens can be used as a magnifier, then L3 is a converging lens. Now we still have the lens L4. Let me make some space here. The lens L4 corresponding to document 4. Okay, in this document the direction of propagation is from right to left, and we have that the emergent ray and the object focus are on the same side, and we know that this is the case of a diverging lens, because in the diverging lens we have that the emergent ray and the object focus are always on the same side. For a diverging lens, the emergent ray and the object focus are on the same side. Therefore, then L4 is a diverging lens. Okay, so this is it for exercise number 2. Okay, so now we have reached exercise 3. Document 1 shows a lens L, its optical axis x prime x. F is the focal length of this lens and F is the object focus. So number 1, they are telling me O is the optical center of L, justify. Notice that the point O represents the intersection between the optical axis and the lens L, therefore the point O is the optical center of the lens. Then let's write down O is the optical center because it is the intersection between the optical axis and the lens L. And now in number 2 they are telling me redraw with the same scale the figure of document 1. So notice that here the direction of propagation of light is from left to right. And whenever we need to redraw, we always start by drawing the optical axis at the middle, having the same direction of propagation of light. So this is x prime and this is x. And then we place the lens L perpendicular to the optical axis at the center. Using the correct symbol, in this case the symbol of a converging lens. And the point of intersection between the optical axis and the lens L is the optical center, O. Now the object focus F is located 1, 2, 3, 3.5 divisions in front of the lens. So 1, 2, 3, 3.5. This is the position of the object focus F. And the scale along the x-axis is given by 6 centimeters. So this is it for part 2. Now we have reached part 3. Now in number 3 they are telling me let F be the focal length of L, 3.1. Specify the position of the image focus F prime. So the word specify means that we need to justify. So we know the position of the object focus F, then we can directly deduce the position of the image focus F prime because we know that F and F prime are symmetric with respect to the optical center O. So 1, 2, 3, 3.5. This is the position of the image focus F prime. And the justification is given by that F and F prime are symmetric with respect to O. Now in 3.2 they are telling me deduce F, and the word deduce means that I need to use the part just previously before. In 3.1 we have determined the position of the image focus F prime, and we already know the position of the optical center. Therefore now we can deduce the focal length graphically by referring to its definition, and which is given by the focal length is the distance from the optical center to the image focus. So the focal length denoted by small f is equal to the distance from the optical center, which is the point O, to the image focus, which is the point F prime. And we don't forget the bar because this distance may be positive or negative. So now F is equal to O F prime bar, which is the distance from the optical center to the image focus. Notice that this distance is in the same direction of the positive x-axis, therefore the focal length is positive. And now we count the number of divisions between O and F prime. We have 1, 2, 3, 3.5. and we multiply by the scale along which we have counted the number of divisions, which is scale along the x-axis, and this will give me 21. Since the scale is in centimeters, then the value of f will be in centimeters. Always, all quantities in physics must have unit. Finally, it's a good habit to write our final answer in a box to make the task easier for the corrector to notice our correct answer. So notice that the focal length in this case it's positive, and from the symbol of the lens we know that the used lens is a converging lens, so the focal length is positive, which verifies that the used lens L is a converging lens, because we know that for a converging lens the focal length is always positive. So this is it for exercise number 3. We have reached section 5. The title of this section is Construction of the path of luminous rays. Previously we have seen the effect of a converging lens and a diverging lens as well on light rays. In the case of a converging lens, the emergent ray emerges toward the optical axis, and in the case of a diverging lens, the emergent ray emerges away from the optical axis. And now in this section we will see the effect of each on specific light rays. Let's start by the converging lens. For a converging lens, let me write down. In order to see the effect of a converging lens on these specific light rays, first we need to construct the optical system. So as usual, we always start by taking the direction of propagation of light to be from left to right. Then we place the optical axis at the center, having the same direction of that of propagation of light. This is the optical axis. X prime x. Then we place the lens L perpendicular to the optical axis at the center using the correct symbol. Here we are concerned about a converging lens. This is the symbol of a converging lens. And the intersection between the optical axis and the lens L is the optical center O. Moreover, now we need to place the object focus and the image focus. Because the direction of propagation of light is from left to right, and the lens that I'm using is a converging lens, then we place the object focus to be on the left and the image focus to be on the right, symmetric with respect to the optical center. Okay, so now let's construct these specific rays. The first one that we need to consider is an incident ray parallel to the optical axis. Because the direction of propagation is from left to right, then light will only be allowed to travel from left to right. The first one is parallel to the optical axis. This is the incident ray, and we don't forget arrows on light rays. By definition, an incident ray parallel to the optical axis, it emerges passing through the image focus f prime. Okay? Recall that we call this ray to be the incident ray because it's hitting the lens, and this ray to be the emergent ray because it's coming out from the lens. The title of this section is Construction, and construction in optics means that we need to trace and justify at the same time. What we have done here is a tracing of the path of an incident ray parallel to the optical axis. Okay, and construction means that I need to trace and to justify. Now let's justify the path of this ray. An incident ray parallel to the optical axis emerges. Okay, it emerged passing through the image focus. Then this is the justification of ray number 1. Now the next ray that we need to trace and justify is the one passing through the optical center. This is a ray passing through the optical center, an incident ray. By definition, this ray will emerge without changing its direction, or in other words, without deviation. Now what we have done here is the tracing of ray number 2. Now let's justify its path. An incident ray passing through the optical center emerges without deviation. And I repeat that here the word without deviation means without changing its direction. Notice that here the second ray, the one that is passing through the optical center, it didn't change its direction. The third ray and the final one that we need to consider is passing through the object focus. So consider an incident ray passing through the object focus. By definition, this ray emerges parallel to the optical axis. So opposite to ray number 1. And we don't forget arrows on light rays. So this is number 3. The way to memorize these rays is that always an incident ray parallel to the optical axis is related to the image focus. Incident ray parallel to the optical axis is related to the image focus. And an incident ray passing through the object focus is parallel to the optical axis. Okay? So now the justification, this is the tracing of the third parallel, this is the tracing of the third incident ray. Now let's justify its path. Why? Because I repeat, the title of this section is construction. So we need to trace and justify at the same time. An incident ray passing through the object focus emerges parallel to the optical axis okay. So these are the construction of the path of luminous rays for a converging lens. Okay, the rules are that the incident ray, parallel incident ray, is related to the image focus. The one passing through the optical center emerges without deviation, and the one passing through the object focus emerges parallel to the optical axis. We will apply the same rules here for a diverging lens. Then let's do the same for a diverging lens. Okay, we always start by taking because we need to construct the optical system. So let's start by taking the direction of propagation of light to be from left to right. Then the optical axis will have the same direction. And we place the lens perpendicular to the optical axis at the center. Okay, here we are constructing the optical system of a diverging lens. We use the correct symbol. Let's label some stuff. This is the lens L. This is x prime, x, and the intersection between the optical axis and the lens L is the optical center O. Now we need to place the foci of the lens L, because the lens L that we are using is a diverging lens and the direction of propagation of light is from left to right. Then we place the image focus to be on the left and the object focus to be on the right. Here we will consider the three rays that we considered for a converging lens. Then the first one is parallel to the optical axis. And we know the rule is that always the incident ray parallel to the optical axis is related to the image focus. Incident ray parallel to the optical axis is related to the image focus. But because the direction of propagation of light is from left to right, light cannot travel backward to pass through the image focus. Light will travel to the right because the direction is from left to right. So, as we can notice that light cannot pass through the image focus because it cannot travel backward. The trick is that the ray will emerge from the lens as if coming from the image focus. Because this light ray cannot pass through the image focus, it will emerge from the lens as if coming from the image focus. Okay, now this is the tracing of this ray. Now let's justify its path. An incident ray, this is the case of a diverging lens. An incident ray parallel to the optical axis emerges as if coming the image focus. And here the dotted line, it represents that the light is coming from the image focus. Now the second ray that we need to consider is passing through the optical center. First let's trace it, then we will justify. Okay, passing through the optical center. Here nothing will change. It emerges without deviation. And we don't forget arrows. Now let's justify. An incident ray passing through the optical center emerges without deviation. And finally, the last ray, incident ray that we need to consider is passing through the object focus. Now, this is the region here, this is the region of the incident ray. Then we need to draw an incident ray passing through the object focus. But notice that the object focus on the opposite side of the lens. So here it's behind the lens and this is in front of the lens. The object focus is behind the lens and not in the same side or the same region of the incident ray. Then we cannot draw an incident ray passing through the object focus. But here the trick that we will do is that we will draw the incident ray directed toward the object focus. So we will do the same trick that we have done for the first incident ray. Because the incident ray cannot pass through the object focus, then we will draw it as if directed toward the object focus, like this. And the rule says that always incident ray with the object focus, it emerges parallel to the optical axis. So this is the second ray here, and this is the third ray. Now this is the tracing of the third ray. Now let's justify it. An incident ray this incident ray is not passing through the object focus, is directed toward the object focus. Directed toward the object focus. Emerges in this case parallel to the optical axis. Okay, so this is the construction of the path of luminous rays, and we have finished section 5. So that's it for me in this video, guys. In part 3 we will solve an exercise about this section, which is section 5, and complete the explanation of this chapter.